Good day, students. Welcome to question number 5 of our 2014 AP exam review. In this problem, we're going to be focusing mainly on solving problems involving sign charts, connecting the graph of f and g to their derivatives, and also the mean value theorem. Don't forget to visit math.serve.com under AP Calculus to gain access to the remainder of the videos on this review series. All right, let's take a look at the A part. The A part of number 5, let me go ahead and write down the number here. This is number 5. Says find the x-coordinates of each relative minimum of f on the interval from -2 to 3. So for the entire function, remember we're just focusing on f. Where do we have a relative minimum? You have a relative minimum when f changes from decreasing to increasing. Okay, so we have a relative minimum at, let's say, C if f changes from decreasing to increasing. Okay, so basically the function looks something like this. If you have that, then you have a relative minimum. But how about the first derivative? What happens with the first derivative to indicate the existence of a relative min? We know we have, when you have a relative minimum, you have, that's also considered a critical point. So the derivative, of course, is going to be 0 at that point, but what happens with the derivative before and after that point? If a function is decreasing, we know that the derivative is going to be negative. Okay, so if f is let's do decreasing first. Do this. F is decreasing implies that the derivative is negative. It goes both directions. If the derivative is negative, then the function is also decreasing at that interval. If f is increasing, then the derivative is going to be positive, right? And it also goes both ways. So if f changes from decreasing to increasing, it also follows that the derivative f prime changes from what to what? It changes from negative to positive. All right? So we do not know what the graph looks like here, so we do not know where it's increasing or decreasing. But what we do have is the information about the derivative, the first derivative, and that is sufficient to help us describe the behavior of the function, the graph of the function f. All right? So if f prime is negative here, that means f is going to be doing what? Decreasing. If f prime is negative on this interval, that means it's going to be decreasing. If f prime is positive on this interval, that means f is going to be increasing. Okay, so you see it's decreasing, decreasing, and then increasing. Even though you have a critical point at -1, it's not the minimum because it decreases, probably flatlines, and then it continues decreasing. And then here, actually, when the derivative becomes 0, it turns around and it starts to increase. All right, so at what x value does the derivative change from positive to negative? It happens at x equals 1. So what does that mean? It means that you have a relative minimum at x equals 1. Okay, so let's go ahead and write down the answer. So we have f of x has a relative minimum at x equals 1 because remember we are asked to provide justification here, so it's imperative that we do that because f prime of x changes from negative to positive at that x value. okay, at that x value, and we know what that means. Okay, so that's that. All right, let's take a look at the B part. It says explain why there must be a c for -1 less than c less than 1, such that the second derivative of f at c is equal to 0. All right, we do not have the graph of f prime here, so we're basically trying to use f. We don't have the graph of f double prime or any information about it, but we're using f prime to form some conclusions about f double prime. At f double prime of c equals 0, what does this mean? This is basically telling us that the instantaneous rate of change, also known as the derivative, at some c between -1 and 1 is equal to 0. So when you're finding the instantaneous rate of change on a closed interval, what can you use to approximate it? And in certain cases, there's a theorem that actually tells you that the instantaneous rate of change attains a certain value on an interval of a continuous function on the closed interval. Do you remember what that theorem is? It is a mean value theorem, okay? So we're going to be using the mean value theorem here. So for the mean value theorem, it basically tells us that if f, let's use f prime. If f prime is continuous on AB and differentiable on the open interval AB, then there exists a C in the open interval AB where the slope of the secant line, which is f prime of B minus f prime of A over B minus A, is equal to the instantaneous rate of change, which is f prime of C. So this is a mean value theorem, but the only difference here is that f double prime of C, I'm sorry. The only difference here is that I'm using, instead of f and f prime, I'm using f prime and f double prime. All right? So in this problem, we can apply the mean value theorem here, because you'll see that when we find the slope of the secant line from -1 to 1, we're going to get the solution, which is 0. All right? So let's see if we can, if this statement is true. So in order for this statement to be true, the slope of the secant line on this interval must be equal to 0. All right, so we know that f double prime of c is equal to 0. That's given. All right, now we have to show that the average rate of change of the slope of the secant line on that interval is also equal to 0. All right, so f prime of B minus f prime of A over B minus A, the slope of a secant line, is going to be equal to f prime of -1 minus f prime of 1 over -1 minus 1. This is the slope of the secant line of the graph of f prime on the interval -1 to 1, okay? Or the average rate of change. So let's go ahead and figure out what this is. Using our table, f prime of -1 is 0, f of 1 is 0. So we're going to have 0 minus 0 over -2, which is equal to 0. Okay? So since this function is continuous on that interval and differentiable on that interval, there exists some c in that closed interval where the instantaneous rate of change f double prime of c is equal to 0. Okay, so let's go ahead and write this down. Since f prime is continuous on the closed interval -1 to 1 and differentiable, we're told in the problem all these facts. We're told that the function is double differentiable, so it automatically implies continuity for the first and second derivative, all right? So since f prime is continuous on negative 1 to 1 and differentiable on uh, negative 1 to 1, which is a subset of negative 1 to 1 with the endpoints included, and the average um, rate of change um, is negative 1, I'm sorry, the average rate of change is what? Is 0. The average rate of change is 0. Then there exists a C in the open interval negative 1, less than C, less than negative 1 less than x less than 1. There exists a C in this interval where the instantaneous rate of change of the first derivative, which is f double prime, the derivative of the first derivative. So there has to be a C where the instantaneous rate of change is equal to the value of the average rate of change, which is 0. Okay? So using the mean value theorem, it's a little bit longer, but you can use Rolle's theorem to conclude this real quickly. With Rolle's theorem, since f of a is equal to f of b, then you can just conclude by Rolle's theorem that there is a C where f prime of C is equal to 0. Rolle's theorem is much more direct. I like this one because it shows you a lot of processes going on with the mathematics. But Rolle's theorem is basically an extension of is a special case of the mean value theorem. All right, let's take a look at the C part. It says the function h is defined by h of x equals the natural logarithm of f of x. Find h prime of 3. Show the computations that lead to your answer. So h of x is equal to the natural logarithm of f of x. So if you find the derivative of this function, h prime of x, what do you notice here? You notice that you have a composite function. So anytime you have a composite function, you want to use the chain rule, okay? So if I apply the chain rule here, the derivative of the natural logarithm of u is going to be 1 over u, which is 1 over f of x, where u is f of x, times the derivative of u prime, which is f prime of x. All right, so now we want to find the derivative at a fixed point, namely at x equals 3. So h of 3, h prime of 3 is going to be what you get when you evaluate the derivative at x equals 3. So we're going to have 1 over f of 3 times f prime of 3. So we're going to be using the f column and the f prime column, evaluating them at x equals 3. So f of 3 is 7, f prime of 3 is 1/2. Okay, so let's go ahead and plug it into this function here. So we're going to have 1 over 7 times f prime of 3, 1/2. Multiply them together, your answer is 1 over 14. All right, let's take a look at the d part. We have to evaluate the definite integral of f prime of g of x times g prime of x dx. So basically this is undoing the chain rule. Okay, so remember the chain rule, the derivative d dx of f of g of x. If you differentiate f of g of x, you're going to have f prime of g of x times g prime of x. That's the chain rule, right? So what if you found the antiderivative of both sides of this equation? You're basically trying to undo everything, okay? So what we're going to do is multiply both sides by dx. If we multiply both sides by dx, we're going to have, let me show you my work, multiply, kind of like solving a differential equation by separation of variables. So if you multiply both sides by dx, you have df of g of x, right, equals f prime of g of x times g prime of x dx. All right, and then if you integrate both sides like that, So just look at this as a variable like dy. Okay, you can think about this as dy, and then if you integrate 1 dy, what do you end up with? You just end up with y, right? So on the left side, this is simply going to be f of g of x equals the integral of f prime of g of x times g prime of x. Study this, the right side of this equation for a second. Isn't that exactly what we have here? That's what we have. Okay, so this is basically the reverse of the chain rule. You're integrating the result of the chain rule. All right, so if you integrate the result of the chain rule, you end up with the composite function f of g of x. So let's go ahead and apply it, this idea to this problem. So the problem asks us to find the definite integral from -2 to 3 of f prime of g of x times g prime of x. So the antiderivative of the derivative of a composite function is the composite function f of g of x evaluated at its limits of integration -2 to 3. Alright, so using FTC part 1, we're going to plug in the limits of integration. We have f of g of 3 minus f of g of 2, I'm sorry, -2. Alright, so we're going to be making use of the f and the g rows in computing the value of this expression. So let's go up to find, we have to find g of 3 and g of -2 first. So let's go ahead and find that. G of 3 is 1, g of -2 is -1. So we're going to plug that in first. So we're going to have f of 1 minus f of -1. Okay, now we're going to switch to the f column. All right, so we're going to find f of 1 and f of -1. So f of 1 is 2, f of -1 is 8. So we're going to put that back in. F of 1 is 2 minus f of -1, which is 8. 2 minus 8 is -6, and that's the value of the definite integral of f prime of g of x times g prime of x from -2 to 3. Alright, so that's that. So thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to other great calculus clips such as this. Please post a comment in the comment section to let us know what you think about this tutorial. And do give us a thumbs up and a favorite if you liked it. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day.